All right, so here is a two-dimensional frame with non-rectangular configuration under a point load of 30 kilonewtons. So I want to solve this using slope deflections. So the first thing is to draw the deflection shape. So this point D, I expect to move in a direction which is perpendicular to dB because of actually inextensible assumption for dB. And this is a very, very small deflection. So I'm expecting to see this point move horizontally. And I'm also expecting this point to move perpendicular to AC. Perpendicular to AC, to that point. And I also know that because actually inextensible assumption for CD, then point C should move horizontally with an amount which is the same as the horizontal movement of the D. They should be moving with the same amount in order to comply with the actually inextensible assumptions. All right, so with that, then I can draw the possible deformation shapes. This is going from here to here, and then there, goes up. Maybe something like this. So this is a possible deflected shape. So now the rest of the calculation is trying to calculate how much it moved, delta, as well as how much this point rotation angle, theta c, and rotation angle, theta d. So we do have three unknowns that we need to find. So if I know the three unknown, the rotation angle and the translations, then I can use them, substituting them into slope deflection equations and getting the end moments. And from end moments, I can get shear force. Then I can go plot shear force bending moment diagrams. So the first step is trying to get these unknown comes out. Now, imagine this. How many equations you can use or you can establish? Imagine this. I should have one joint equilibrium here. Summation M at C should be equal to 0. That's one condition I can use. The second condition will be coming from summation M at D equal to 0. So I should have two joint equilibriums comes out. So the question is, where is the third equation going to come out to help you solve for the three unknowns? So let me just put it down. All right, I need one more. So where is that one coming from? So who can give me the answer? Local, global equilibriums. All right, yep. Global equilibriums, but in what sense? Now, previously, now if this is this, if this is like that, it's very similar, except that it's rectangular. So this is what we will do. I establish equilibriums here, equilibrium there. That gives me two conditions. And then I calculate shear force. And using the shear force will be functions of n moments. So it will be functions of unknown. So the two shear force add up equilibrium, and that's it. That will be the third equation, right? But this apparently is more complicated. Can we do the same thing like there? Can we set up shear force and shear force? Can we do that? If yes, then this shear force plus that shear force equal to that. Then that will be our third equations. But is that possible? The answer is no, it's not possible. Why? It's possible on this component because this component is perpendicular. But it's not possible for this component. Let me show you why it's not possible. So here is a component AC. So I'm supposing to get this and this. So this is 2EI over LAC. 2 times theta A, 2 times theta C, 1 times theta A, which is equal to 0, 3 times minus 3 times rigid body rotations, like that. And here, this is 2EI over L, 2 times theta A, 1 times theta C, 3 times rigid body rotations, like that. So I can set up these two end moments, no problems. It will be functions of theta C as well as rigid body rotation angle. So I just need to figure out what is the rigid body rotation angle. So this is going to be the rigid body rotation angle. And you can see that it's going to be functions of delta. So I can set this up, set that up, no problems. But can I find, similar to that, the shear force? So what do you think? Can I find this force? The answer is no, you cannot find that force. You can find this force, but you cannot find that force. This is BD. So this is the BD component. It's perpendicular. So can I find this force? Yes, I can find that because all I need to do is come over here, take summation M D. Summation M D. Then they should have an actual force. They are forces like that acting on a component. So if I come over here, take summation M at D, then this moment is there, this moment is there. This force is not contributing, this force is not contributing, this force is not contributing. Only this force will contribute to the moment. So as a result, this force is going to be functions of MdB and MbD. So you can get that, no problems. Can you see that? I don't want to just give you the equations without explaining. I want you to visualize and see it for yourself. Yes, so you can get that force, no problem. But you can see that this force now is not possible to get because coming with that force is this force, perpendicular. So there will be this force and that force. So if you come over here, take a moment, then this is going to be 0, this is going to be 0, but this is not going to be 0, this is not going to be 0. So you cannot find this force as a function of MAC and MCA directly, because there's another force there which contribute to the moment. So you cannot. All right, you see that? OK, so you cannot get that, but I can get this, though. I can get the force which is perpendicular to the members, because the other force is going to be perpendicular to that. So I can get this force, though, because this force contribution is going to be equal to 0. So I can get that force. So instead of this force, I can get this force. So this force is going to be functions of MAC and MCA, which are functions of rotation angle and translations. All right, so I can get that. It's supposed to be 90 degrees. This is the shear force of that member. So this force I can get, and it will be functions of rotation angle and translations. This force I can get functions of rotation angle and translations. So can I formulate another equations, global equilibriums, so that I can put it here? Help me to solve for the 3 unknowns. That's the problem, all right? So it turns out that, yes, we can do that. Let me show you. It's a little bit tricky, but it can be done. So just imagine now I have a force, applied force externally. On this leg, I have this force, which is not known. I don't know. Perpendicular, I have a way to find out. Perpendicular, I have a way to find out. Vertical, I don't know. So I want to set up one additional equations from this so that I can put it there to help me solve problems. So the answer is yes, but you have to do it intelligently. You have to extend this line, extend this line. All right. You find this point intersecting of the extensions of 2 lines, and you do summations M0 equal to 0, global equilibrium. So if you do that, then you will take this force in. You will take this force in. You will take this force in, but not this force, not that force. Of course, you will also take this bending moment in and this bending moment in as well. That's the tricky part of these questions. So how do you set up the third equilibriums or the third conditions to help you solve for the 3 unknowns? So the answer is here. It seems to be the only way out. You're trying to establish one equilibriums at far away point, which is the intersections of the 2 extensions line. And the reason for that is you're trying to eliminate this force as well as that force from getting into the equations, because these 2 forces cannot be very cleanly expressed as a functions of the 3 unknowns. But these 2 forces can, as well as the M moment. So altogether, you set up summation M0 equal to 0. So here, let me put it down. Eventually, we're going to use summation M0 equal to 0. and our condition is met. Okay, so that is the solution, the logic behind the solutions. All right, so let's try to piece them together one by one. So the first thing you need to do is to come out with a rigid body rotation angle. So this is beta 1. This is beta 1 according to trigonometry. So this is going to be delta divided by cosine beta 1, which give you this one. So delta divided by cosine beta 1. And the length of AC is 20. And it's in the clockwise direction, so be negative. – 16/20. So that's rigid body rotation angle for AC. So rigid body rotation angle for BD. BD is easy. It's just delta divided by length. Clockwise. And rigid body rotation angle for CD. So connecting two points. So here, this is the rigid body rotation angle. So it's going to be this height divided by the length. So height is there. So it's delta tangent beta 1. Delta tangent beta 1 over the length, 20. And it's counterclockwise, so it's positive. I don't think you can memorize this. It just depends on your understanding about inextensibility of the components and trigonometry. So there's no use to memorize all these equations. It's not going to help you. OK, so with that, then we are ready to formulate one by one. So let's go to C. So this is joint C. So this is AC component. This is CD component. So this is MCA. MCA, MCD. So the joint looks like that. So here, this is MCA. It's going to be 2EI over LCD. 2 times theta C, 1 times theta A. You? Questions? Oh, yeah, thank you. CA. 2 times theta C and 3 times rigid body rotations. No fixed end moment. And this is MCD. 2 times EI, LCD, 2 times theta C, 1 times theta D, 3 times rigid body rotation angle, no fixed end moment. All right, so the joint equilibrium say that this plus that should be equal to 0. So this, that. OK, that's the first equation. So let me give you the first equations explicitly. The first equation is 4 theta C, theta D, that's the first equation. All right, second equations, you follow the same approach. Follow the same approach. So I'm going to just give you the second equation. This is the first equation. The second equation is performing on joint D. Same approach. Second equation. All right, the third equation, like I explained, I'm going to find the shear force and the shear force there. And then I'm going to get summation M0 at the far away point, intersections of these two extensions there, and then do summation M0. That will include 30 kilonewtons as well as this force, and n moments. So quite a lot of force there. So I'm not going to give you the detail, just give you equations that you can go home and verify. So this is the equation coming out from summation M0 equal to 0. Please go home and verify this. So with the three equations, then we can find all right, so we can find the three unknowns. Yeah? Which one is what? Okay. All right. I don't need my notes for that. This is M dB, and this is M dC. So this equation is from summations M dC plus M dB equal to 0. So it's here. So now you just need to figure out what is MDC and what is NDB. All following this slope deflection equations. 2EI over L, bracket, 2 theta I plus 1 theta J minus 3 times rigid body rotation angle and fixed end. So just follow that equations. You should be able to set this up, which goes there. OK? Now, how about the third one? I hope you still remember. This is what I said. The third one should be established like this. So you should be able to find this moment, and you should be able to find shear force, which is perpendicular to that component, shear force, which is perpendicular to that component. And you need to use trigonometry to set up to find this point, and there's an external force of 30 there. Cool? Very cool. So maybe to help you out a bit, I'm hoping that you will do this at home. Maybe I give you the numbers, help you to all right. So the distance from this point to this O is 33.3 meters. The distance from point D to this point is 26.67, which you can actually establish based on the trigonometry or the information given on the board. Now, I can easily change the problems so I can easily change the problems by maybe now previously we have this problem. So we have this problem. Now I can change I can just change the loadings. How's that? So I can modify my problems very quickly. so you get into trouble very quickly, right? Okay. So I can also do it this way. So I can say that I apply a loading of bending moments there. How's that? So I can also do some force like this. Or I can do forces like that. So there will be a lot of variations, possibilities. Well, anyway. All right, so do you have any questions about this? So after getting that, all you need to do is come back to slope deflections, substituting them one by one. Then you get the n moments for all the components, and then calculating a shear force and plot them out, shear force bending moment diagrams. Okay, any questions? If not, let's move to the last chapter now, called moment distributions. Ready? Let's go. Now, moment distributions, it works like this. The methods skip completely the calculations of deformations. This is deformations. And we spend a lot of efforts trying to solve for the unknowns through simultaneous equations. But for moment distributions, they go directly to moment, skipping completely the calculations of deformations. So that's why it's very, very efficient. So let me show you the concept. It's based on slope deflection equations.